So, welcome back to our course on projective geometry. This time I want to show you two important incidence theorems, and there's at least a threefold reason for presenting you those two theorems here. One of them is, I want to introduce you to the concept of what is an incidence theorem, because this is a very important concept in projective geometry. Secondly, I want to show you these two theorems because they are very, very far-reaching concepts in real projective geometry. And the third reason is, these two theorems are among the most beautiful structures that I know in projective geometry, so you simply have to see them. So, what are those two theorems? So, one of them is this guy here, and it dates back to Pappus of Alexandria. We are in the year 350 AD, so it's a really early discovery in projective theorem, and it's some statement about altogether 9 points in the projective plane, essentially stating if those three points are collinear and those 3 points are collinear, and you make those crosswise intersections here, then they will be automatically collinear as well. Clearly, Pappus of Alexandria didn't state that in the projective plane, but the concept of this theorem can be traced back to him. The second theorem is somehow from the late Renaissance period, and it's due to Desargues, a French mathematician, and it's in flavor very similar, but now it's a theorem on altogether 10 points, saying, well, if you start with those 7 points and have all those collinearity here, then you will get the last one here for free. And so let me first start with a very general setup, telling you what I consider to be an incidence theorem, and Pappus and Desargues are essentially two special cases of that concept. So the concept of an incidence theorem is, I would say, the projective equivalent of a theorem in elementary geometry. If you have this and that and that, then you automatically have that. Now, our language that we have in projective geometry so far is extremely elementary. We only can speak about points and lines and incidences. So an incidence theorem is something that can be traced back or completely stated in terms of points, lines, and incidences. So you have a bunch of hypotheses in the theorem. So a standard form, without going into specifica of the theorem, would be certain point sets are collinear, and this is an important point, you also need certain point sets are not collinear, because otherwise things may get too degenerate, you couldn't the theorems simply wouldn't be true in that case. And from those things, from a certain set of collinearity and a certain set of non-collinearities, you make a conclusion, and the conclusion is again another collinearity. So looking for Desargues' theorem, so you have the situation here, you have many collinearities, and you make sure that this situation is not too degenerate. We will see what that means in a minute. Then for free you get the conclusion, another collinearity in that game. So let me start with the theorem of Desargues, and first of all make the statement in a way that it fits into the framework of an incidence theorem. So, these are the collinearities that I assume to hold. So I labeled my points here from 0 to 9. So 0 I included here because you have 10 points. And if you label from 0 to 9, you can get away with one-digit numbers. And so the collinearities you want to have are, for instance, 0, 1, 4. You see 0, 1, 4 is a collinearity in this picture, 0, 2, 5 is another one, and so on and so on. So you have 9 collinearities. And I don't make that specific yet, you have certain non-degeneracy conditions, meaning that well, not too many of those points have additional collinearities. So one very generic non-degeneracy condition you may think of is that no pair of blue lines coincides to be one line. And if you have all that, then automatically 7, 8, 9 turns out to be collinear as well. I want to show you that these non-degeneracy conditions are really essential, and for that I do the following thing. Well, I took some of my points here and put them all on a line. So you see, for instance, 3, 6, 0 is a collinearity, and you have it here, and 2, 3, 8 is a collinearity, and you have it here. So many collinearities here are satisfied just by this bunch of collinear points. And now this violates my generic non-degeneracy conditions. Some of the lines here now really coincide. And now I want to show you what happens if you do that. So you can check carefully that this configuration here really satisfies all the collinearity conditions here, but not our generic non-degeneracy assumptions. But you see the line 7, 8, 9 finally turns out not to be collinear. Actually, as you see here, you can move 0.8 arbitrarily on that line, and you won't, and you will only have one position where it actually gets collinear. So you see, these non-degeneracy conditions are really an important ingredient. So the main reasons for them is, if you write down an algebraic proof of your theorem, then every now and then you may divide by a number, and you know it's forbidden to divide by 0, and those degeneracies here force you to divide by 0. So let me continue with Desargues' theorem, and I want to give you a simple proof of the theorem. Well, I first move my points around a little bit, so you see, well, it's actually, well, you see here our point here really always stays nicely on that line. So now you've seen many examples of the theorem, but you haven't seen a proof yet. And for the proof, I want to do something that isn't, I would say, that isn't projective in its entire nature, but it's still in the projective framework. So we have those 2 points here, and you see those lines here meet at a very narrow angle, and it may be a good strategy to go to a special position where I move those 2 points to infinity. And now I really moved them there. So you see, I'll pick that point and move it far out, and I pick the other point and move it far out. So this is still an instance of Desargues' theorem, just with 2 special positions of points, which can be done without violating generality. So how does it look like when we move now? So let's move our points just a little bit. So one thing you should observe, that now you have 3 parallels here. So you still have so you have a bundle of parallels here and a bundle of parallels here, but you still have a very general quadrangle here, and from there we can formulate a very, very easy proof. So here comes a very easy proof. I've given my lines a little bit color. Those diagonals now are green, and those parallels here are now drawn in orange. And now I do a proof that is essentially something that is, I would say, Euclidean geometry reasoning. So I consider two lengths. One is the length between those 2 points, and the other is the length between those 2 points, and call them A1 and B1. And I consider the ratio between these 2 points. And you see, I divide by B, and being able to divide by B is one of the assumptions that the proof indeed works. And if you look at those 2 points, if B would become 0, then this term here would no longer be defined. Now I consider a different pair of lengths, namely from here to here and from here to here. So you have this length versus this length. And now something interesting happens. So since we are in the situation that this line here is parallel to that, this ratio must be exactly the same as the other ratio. So we consider this triangle, we have this line here parallel to that, and we can conclude those two ratios have to be the same. In the same manner, we can consider the ratio from here to here, and again conclude they must be the same because these two lines are parallel, and the ratio from here to here, and they must be the same because these two lines are similar. So by using this parallel and this parallel and this parallel, we concluded that essentially this ratio here is the same as this one. And now we read the things backwards and conclude, well, if this ratio and this ratio is the same, then this line and this line have to be parallel, and we proved Desargues' theorem. So there are many different proofs of Desargues' theorem, but this is a particularly simple one. So why is Desargues' theorem interesting? And actually, I would love to give an entire lecture just about this theorem here, because, well, it's really a far-reaching thing. So one of the interesting things, it has amazing symmetry properties. So here you see a twofold symmetry of the configuration, but actually the automorphism group of this symmetry has 120 elements. So it's a highly symmetric object, and I will demonstrate that to you in a minute. But before that, I want to show you a few other interesting aspects of the theorem. There are many different ways to approach proving these theorems, and whenever you have several ways to approach the same theorem, this connects fields. So actually the Desargues' theorem is some place where you can connect different areas of mathematics by approaching this theorem from many different angles. There is in particular a very nice proof via three-dimensional reasoning. Actually, the Desargues' theorem is the beginning of a sequence of theorems that are all very interesting. And it has one interesting property. It's a so-called N3 configuration. So N3 configuration are a very special thing. So this is a specific 10-3 configuration, meaning the following thing. You have 10 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And through each of the points, you have exactly 3 lines. And you have 10 lines. And on each of the lines, you have exactly 3 points. So this is a very symmetric case of an incidence theorem. And it's also self-dual. In one of the next slots, we will learn about interchanging concept like points and lines in the projective plane. And actually there is an isomorphism of this, or an automorphism of that theorem, where you map points to lines and lines to points, and many, many, many more things. At least I want to show you one of the items of that list, the amazing symmetry properties. So you should see that none of those points in that picture plays a special role. And for that, to explain you that, I've drawn a picture of, well, a five-gon with all the diagonals in it. So you can also think of it as a complete graph on five nodes. So you have five points here, and you connect each one to each one, and the automorphism group of that picture is obviously the S5. So you can interchange any two nodes and get an automorphism of that graph. And now I tell you a little trick how to get from this the combinatorics of that picture to the combinatorics of Desargues' theorem. And for that, you do the following thing. You label the edges of that picture, and now every triangle in that picture here corresponds to a collinearity of that. So you have altogether 10 lines here, so 10 edges, and they correspond to the 10 points in our picture. And now we look at the triangles. So we take, for instance, this triangle here. It contains 0, 4, and 1. And here we have 0, 4, and 1. And we also have 1, 2, 7. And here we have 1, 2, 7. 7, 8, 9. Here we have 7, 8, 9. And so on, and so on. Then you come to the inner triangles. You have 4, 5, 7. And here you have 4, 5, 7. And so on, and so on. And you see the triangles here correspond exactly to the collinearities on the other side. So both theorems have to have identical automorphism group. So both configurations have to have the same automorphism group. So far about Desargues' theorem, and now I want to come to the theorem of Pappus. So here we have Pappus' theorem, and you see I left these properties here just in the same way, because everything we said about Desargues' theorem can also be said about the theorem of Pappus. It has, again, amazing symmetry properties. It has many different proofs. So the first chapter in the Perspectives of Projective Geometry book is just a collection of different proofs for Pappus' theorem. So I really urge you to read that chapter. It also has, it's a little bit more subtle than the other one, a proof via 3D reasoning. It's a beginning of several very, very interesting theorems. It's also an N3 configuration. Now it is a 9-3 configuration. You have 9 points here, and on each line you have 3 points, and through each point you have 3 lines. So it's again a 9-3 configuration. It's self-dual. There is again such a kind of isomorphism. And I must say I love this theorem even more than Desargues' theorem, because if you look at it, even more properties hold. So it has interesting relation to algebraic curves. It has the following nice properties. It's essentially the smallest incidence theorem that you may have in the real projective plane. Though there is no other incidence theorem that has less points than this one. For all other incidence theorems, you need more points, at least if you are in the real projective planes. And it has some very, very nice relations also to complex geometry. I want to Well, I haven't stated the theorem right now, so let me really give you the construction of the theorem. So what you do is you start with two lines, and on those two lines you define two more points. So you put a point here and you put a point here. So after all, you end up with two pairs of collinear points, say A, B, C and A prime, B prime, C prime. And after that, you draw essentially all connections that can be drawn between points that don't share a common letter. So you draw a connection from A to B prime, from A to B prime, from A prime to B, and so on and so on. And after that, you get these points of intersections and you insert them into the drawing. And when you did that, you already see it here, it turns out that these points are collinear. So how could you algebraically or in terms of projective geometry define those points? They are the meet of two lines here. So that's point X, that's the meet of those two lines. And the two lines again are the join of pairs of points. So you have the incidence relation encoded here. And finally, it turns out that these 3 points are indeed collinearity. Talking for a moment about non-degeneracy conditions here, non-degeneracy conditions here would be that you really can perform those operations here. So things should be not that degenerate that, for instance, B and C prime coincide, or that those two lines coincide. And so as long as you can perform these actions here, then you would get collinearity at the end. Just to convince you that this is indeed true, I want to, well, move my points a little bit around, and you see how nicely the final collinearity stays in place. I won't give you an algebraic proof of it at the moment. There, as I said, there are many in the book. I told you there are amazing symmetry properties here again. Also, this theorem has a very, very high automorphism group. And now I want to at least show you that you have a combinatorial symmetry of order 3 sitting in the as a subgroup here by simply moving the points again around. So I move this here a little bit lower and I move this here a little bit higher up, and then I have to adjust my points still a little bit, and what you see is a configuration that combinatorially has obviously a symmetry like a triangle. So you have these 3 points as outer points of the triangle, something symmetric happening in the middle, and you see a full S3 at least as a subgroup of that theorem. I want to conclude that lecture by giving, well, I wouldn't call it a proof because we will skip many details, but I want to give you a proof, one of the many proofs that you find in the Perspectives on Projective Geometry book that relates this theorem to a very, very deep theorem on algebraic curves. And for that, we start with this drawing here, which at first sight seems to have nothing to do with the theorem of Pappus, and actually it's a drawing of a much more general theorem, and the much more general theorem is the so-called Cayley-Bacharach theorem, which again dates back to the 19th century, and it states the following. So first we have to learn what are these curves that we see here. These are algebraic curves of degree 3, and what it states is as hypotheses first. So we start with three algebraic curves A, B, C that have degree 3 and are in the projective plane, and they pass through the same 8 points. So these 8 points here are those points here, and perhaps I should first explain you what it means to be an algebraic curve of order 3. Well, it means that you have a polynomial equation of degree 3 in your variables x, y, z, and you see here that these here are all possible combinations in which x, y, and z can form a quadratic term, and it turns out there are exactly 10 such summands in such a polynomial. Then you pick parameters a, b, c, and so forth, and you are interested in all x, y, z such that this equation here becomes 0. So it's essentially a generalization of a linear curve, which is a line, a quadratic curve, which will turn out to be a conic, and this here is a so-called cubic curve of degree 3, and there are also curves of degree 4, 5, and so on and so on. And projective geometry is actually the right space to talk about these kind of theorems. So what does this theorem now tell you? You start with 3 such curves, and they should pass through 8 points. And if you look here, you have 10 summands, and you see there is a kind of homogeneous coordinates thing going on here as well. So if you multiply all your parameters a, b, c by the same factor, you will still get the same curve, which in turn tells you that such a curve is determined by 9 points. So you take 8 of those points, here are 8 of those points, the 8 white one, and 1 additional point. So these are the 3 fat points that you have here to control the position of the curve. Now you get 3 curves of degree 3 through those 8 points, and now the theorem tells you then they have 1 more point in common, and this 1 more point in common is this one. I won't prove it to you. The proof is amazingly simple. In general, it really works by just counting degrees of freedom of what's going on here, but I will skip that. Just take that as a theorem, and I want you at least to believe this theorem. So I jiggle my control points a little bit, so you see you still have those 8 points here, and I move one of the curves around, and no matter where I put it, it will still always pass through that point here. I now move the white points to very special positions in which you get many collinearities, and if you move them to the right positions, say here, 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 3 of them are collinear, 3 others are collinear, you get many collinearities, and you adjust your points here, then it turns out that the 3 curves can be considered as a collection of 3 lines. So you have one algebraic curve consisting of those 3 lines, another one consisting of those 3, and another one consisting of those 3. If you now have considered this very special case of the Cayley-Bacharach theorem, you see that, well, you are essentially making a statement about collinearities, and then this statement here, then we have 1 more point in common, finally tells you that the final incidence in this theorem is satisfied as well. Let me conclude by showing you a few more generalizations. So it turns out that, well, if you are a little bit more general in that case, you get other nice theorems. So what you see here is a case where one of the curves, the blue one, is decomposed into a line and a conic, and you see Cayley-Bachelor's theorem still gives us a proof, and you see a theorem about one conic and 7 lines, and this is so-called Pascal's theorem. I already mentioned it in the very beginning of our lectures, and well, there are many more. I just want to conclude that lecture by showing you many more of those theorems. So here you have a theorem about 2 conics and several lines, a theorem about 3 conics and several lines, and. So you get many interesting special cases. So 2 cubics and a conic and a line. And all these things are special cases of the Cayley-Bachelor theorem. And as a matter of fact, Pappus' theorem is one of the, well, most simple and on the other hand most far-reaching specializations of that theorem. With that, I want to conclude my slot on incidence theorem. I hope that I could give you the impression that this is one of the most beautiful areas that we have in projective geometry. See you later.